Conan. Everything good?
Yeah.
I have a question for you.
Yes.
Should I add remove 1 point of the exam instead of
Remove?
5049? After you tell me the question that wasn't unfair, how should I behave with that?
Yeah, we can discuss about it after the class. Yeah.
That's something I need to.
Yeah.
You go yesterday to the talk that Bob died.
No, I was not here.
It was okay.
I wanted to see it, but yeah, I know he's good. He's good.
I remember you talking about him.
Yeah, yeah. Good morning. Thank you for coming, despite the rain. But remember, it's the water that's moving the sediment, so we need that rain to talk about our sedimentology. Well, unless we stick with the wind. But, will be just part of the story. So while the computer is warming, do you have questions about the previous lecture? If you remember what was about. It's about the wind and the alluvial fans and the lakes. We just started the lacustrine systems, what we call them. Lacustrine depositional systems, and we continue with that, and we'll get into the fluvial systems today. Okay. Still warming. Did you start the source to sink? Did you look at those instructions and what river you have assigned? Yeah, try to do that kind of even the whole project, first half of the semester, even if it's due at the very end. Because the second half after the spring break, we'll discuss about carbonate rocks, like limestones. And the exercise is not about that, it's mostly applied to the first half. So you can probably finish it right after the spring break, will be easier for you. I would like to add the carbonate section to that exercise, but I'm not sure very well how to do that. You can give me some hints maybe during the class or at the end of the class. How to add a carbonate module to your exercise. Let me open it here. Okay. Already too many lectures we have. Don't forget from time to time to ask, why is this relevant to us as petroleum geologists? Did you take any reservoir geology? Or do you have to take? Do you remember? That might be your third geology classes, if that will happen. So that will be more applied, let's say. It used to be in our department someone was teaching that, but I'm not sure, it kind of disappeared, so I'm not sure if you still have to take it or not in a petroleum department. Okay. So we discussed about these different environments with the idea that maybe here. So, so we discussed this deposition environments after we had those the way the sediment transport and the rocks are formed, with the idea that within your field, when you will start working, the interpretation of the depositional systems will be a key to understand the, let's say, the reservoir geometry and eventually the properties of the rock. So it's about prediction. Now we discuss about all of this that they're called the Aeolian systems, lacustrine you have here, alluvial ponds, and the fluvial. They're in general called non-marine systems. Okay, so they're part of the continental. We stop somewhere here. There are different type of lakes according to their origin, and they're volcanic. Oh wait, maybe it was one going back one slide. So to be sure we kind of connect the previous lecture. So one was on the origin, but the most important, and we look at this animation if you remember right after we finished the previous lecture, and the idea is just the continents are moving around and then open and close the oceans. At the time of the opening of the ocean, we might have some lake systems which become large and turn into the oceans. The same thing when you close the ocean, you isolate the parts of the ocean and they turn into lacustrine systems that have been isolated from the ocean. And again, you will discover probably throughout your career that some of these lake systems are quite prolific hydrocarbon systems. Okay. And rift basins are some of this type, and they're in the modern we have in East African area or Baikal. There's some strike slips that you learn about that when the plates are moving, like passing each other. And examples of that is like Dead Sea, for example, or Jordan Valley there. And then again, compressional settings, parts where continents are coming together. And then there are some large basins. In the modern will be Caspian Sea, for example. It's well known, the Caspian and all the area around this good hydrocarbon province. And there are a lot of reservoir there, lacustrine actually, Miocene age. And then there are other areas onto the continents. So other origins, maybe less importance in terms of the size would be like volcanic origin, so or impact craters, so they're calderas that they're filled with water and they form lakes. I mean, small in areas, and also there are glacier lakes. So the Great Lakes, so the North America here, with the names of all of these lakes, they're actually glacier scours that now they're filled with water. And then they form lakes. We'll go over some of these examples so you have an idea about difference in morphology that is linked with their origin. So again, where some of these systems happen in the modern geography, if you want, is where these gray areas are what we call closed drainage basins. So whatever precipitation is falling into this area, they go not into the ocean but into some lake systems. So again, the rift lakes is linked with the rifting of the continents, and here it's an image of a paleogeographic reconstruction. So when the Atlantic was opening, all of these areas here between North America and Africa, and then South America and Africa, all of these were initially rifts, and they were forming rift lakes, and they had their own kind of history of the filling with sediments or stratigraphy. On the both sides of the Atlantic, when you hear, well, there's like West Africa or offshore South America, when they go after prospects, some of them are Cretaceous age lacustrine rocks. So what is typical for this rift basins, because they're linked with the kind of a crust, the crust breakout, they will have this elongated geometries. Here it's a Baikal lake. It's what they call a kind of stopped rift in Asia, and they're elongated and very deep. So what is emphasized here on the slide is that the lake is 1,700 meters deep. It's like as deep as an ocean, but it's in the middle of the continent here in Asia, and it's going probably below the ocean level. So its elevation is about 500 meters, 550 there, the water level. So the part of this kind of eastern part of Asia at one point was kind of opening, I think in Miocene, was starting to kind of break apart and then stop. And then Baikal remained as a lake now, a rift lake. So other examples of this rift basins is what's happening in East Africa. We have here a map of the whole Africa, focus on the eastern side. So it's a rift that's opening here from the southern part of the Red Sea, taking part of the East Africa away, and it's coming back here into the Indian Ocean. So all of these areas, it's a lot of volcanism around that area, but at the same time, Africa is kind of breaking apart, forming these rift systems. And the lakes there, they're also elongated, like you saw in case of Baikal, and they're really deep. Not as deep as Lake Baikal, which I put it there because it's the deepest lake, but they come up to 1,000 meters deep as well. Okay. And there, all of them kind of align along this rift system. So they're bounded by faults, and that's where they're so deep. Okay, they're crustal faults, what they call it. So they go as deep as the thickness of the crust. And some other systems, lake systems that they form now, still linked to the tectonic, but they're not through the rifting. It's mostly from the closing of the ocean basin. So this is the largest that we have now in the still lake is the Caspian Sea. Mediterranean was also isolated at one time and was part of the same systems. The Black Sea, it's almost isolated now. They have just a small strait. Aral Sea, it's another one which is part of all of this Caspian, Black Sea, Mediterranean systems. And I show you this just to get an idea of how different these lake systems are compared with the ocean. It's showing the lake level here. So this is historical time here since 1992 to 2012. So the Aral Sea, what they call it, this lake system, they call it the sea because they're large. So whoever saw it first said, oh, this is like a sea. And then some of these lakes also, they're brackish or they have some salinity in it. They're not quite fresh. They're remnants of the ocean. So the salinity change a bit, but they stay a bit salty. So that some of them are called seas, even they're just kind of closed basins. And it's extreme. Look, since 92, this lake level was dropping 27 meters of the waterfall. And if we look here for the Caspian Sea, which is quite large, is this an image of that? No, this is
That's the Aral Sea now.
This is Aral Sea.
Yeah.
So the Caspian here, it's quite large. If you look on the map, it's more than 1,000 kilometers across, and it's more than 1,000. Well, it's about 1,000 meters deep or so. But the lake level on Caspian also is changing meters, down and up, with the rates of what is saying here. Yeah, will be centimeters, like 13 centimeters per year was raising from 1980s to about 90s, and then start falling again. So that's tens of centimeters per year. Okay, so it's highly dynamic when you consider with the modern ocean comparison. Do you know how much the ocean sea level is rising right now? That we are concerned. Do you know how fast? What will be the rate per year? Say a number. 30 what? 3 centimeters? No, it's within millimeters, I think, per year. Okay, but we're concerned because in the 1,000th year, we might not be wrong. In the 1,000th year, that means meters of the whole ocean rise. It's affecting all of the coastal systems. But in this case, it's going tens of times faster, the lake. So why that's possible? Because the lakes are kind of smaller systems. Okay, so it's easier to, any imbalance of the precipitation evaporation, it's affecting the lake, more dramatically. And in Aral Sea case here, they think it's because irrigation, they kind of stop the rivers to make agriculture. So they stop the river inflow into this lake basin, and then this was the result of dropping. And you see articles about how bad that is, but it's just a closed system with less precipitation coming to it, and it's going out through evaporation. So the glacial lakes, we have good examples into the northern part of North America. They have this elongated geometries, but they will not be as deep as the rift lakes. And their bottom is kind of a smooth, and well, we don't have a cross section here. This is just the bathymetry, so the water depth you see with green and going to blue will be about 200 meters deep here, okay, Lake Michigan. And you see some grooves here. These are given by ice erosion. The ice shields was migrating from north to south as the ice was melting, where it was becoming more dynamic because of the temperature rise after the last glacier maximum. So that was about 10,000 years ago, and they were scouring this the surface of the Earth here. That now it becomes depressions that they close and turn into lakes by collecting the water. You have an idea here about how that happens. So was the ice front was migrating, and when it was doing that, was kind of scouring the base of the ice, was scouring the ground, and when the ice retreated, all the water from the melt, and nowadays from rivers, this keep filling this lakes. Well, these lakes, I think they're connected, at least some of them, with the Atlantic through a series of straits, and at least one of them. Well, this is something else I didn't emphasize. The lakes, because they're isolated, what do you think? Their water level will be the same as the ocean or not? No. So, but is it lower, higher than the ocean? Everyone agreed it's not the same as the ocean, but is it higher than the ocean or lower than the ocean? It can be either. See, the Lake Baikal I mentioned earlier is 500 meters above the ocean level, and the water is spilling out of it. That's an overfilled with water, and has some rivers coming out of it. Okay. The Dead Sea, for example, they call it the sea again, it's salty. The Dead Sea is below the ocean level, I forgot the number.
Tens. It's like 68 meters.
68 meters, I think it's more than that. But it's quite below because it has higher evaporation than precipitation. Okay? So these lakes are more or less at the ocean level. That remind me about this
Maybe 200.
difference.
Maybe 200, I think.
Yeah. So an example here, just briefly to show you. I mean, this was the modern lake system examples, and then the morphology and the origin. So a lake system that some of your older colleagues here in geology, we went out and studied, is called the Green River Lake or Uinta Lake. So there were lake systems into, let's see if we have the state boundary here, it's Utah, Colorado, and this is Wyoming on the map. So it was the lake systems that was going from across some of the states, okay? Utah, Colorado, Wyoming, into Eocene time. So this lake was isolated, okay, completely at that time, and it has a very thick oil shales in it, hundreds of meters. So the conditions were right for high organic production of organic material, and all of that accumulated within this lake basin. Okay. So here there's some numbers on that. So it has like a lot of barrels in place, and it consists of kerogen, precursor of oil. So you have to heat some of this and produce it. But they're very thick outcrops here, hundreds of meters of oil shales. They look whitish here because the hydrocarbon within the rocks oxidized, and it looks whitish on the surface. If you break this, it's black and full of oil. Something special we find when we look close up, like to the rocks faces, what we call it, again, the way the rocks look like, they have something they call varves. So the varves, you have a scale here, so they're very thin, like centimeters or even thinner millimeters, alternating laminae, okay, darker and lighter. So these different colors here, in this case, are caused by the difference in oxygen levels within the lake, like summer, winter. Okay. So to lower the oxygen content in the water, more organic material, and then darker the laminae are. And that's maybe, let's say, during the winter season. In the summer, when the condition changes, it's higher oxygen, then you have less organic and your laminae will be whiter. So you can even count the years here if this is like every season's recording a laminae. So there are different types of varves if you look at. That's what they call this laminae varves, or sometimes they call it lacustrine varves to emphasize in the lakes. But such conditions are common into lake systems, so you don't have them into the ocean, for example. But there are different types. It depends where the lake is and what type of climate. And then you might have this laminae formed by this high-low oxygen changes, but sometimes just when it's windy or less wind, so you accumulate different type of materials, or you record the precipitation, the season, so dry to wet, so you have different type of, let's say, microorganisms that accumulate within the laminae, and that will give them a distinct character. And you can separate them maybe like this in the outcrop or like that. So this thin laminae, again, centimeters or even thinner. Questions about this? Okay, so how do you recognize this? We don't have to go over in detail, but then it's faunal criteria. So there are different type of organisms, as we imagine. We established these lake systems, they're isolated, they have their own sea level, their own conditions of salinity. So because of that, the fauna, whatever fossil material we find within the lacustrine strata or deposits will be different than the, let's say, global ocean at that time. So then their physical criteria, so their substance of tidal currents. We didn't discuss much about tides yet. Do you know tides? Ocean tides, tidal currents? You heard about it. When we discuss the coastal systems, we'll discuss that. But the lakes will have no tides. The waves will not be very large because it's a relatively small surface area of the basin, and the waves will not get very large. You record this seasonality. It's common to have it, this far. And their chemical criteria, so they will form evaporites within lakes, and that's because through evaporation you can increase the salinity and form evaporites. Or they will be brackish or even fresh lakes. A lot of questions. Are these questions helpful to you?
Yes.
Okay, because some of the lectures, they have less questions like that, so I should add more on them so you can get over some of these questions. Oops. We continue with this now. So, questions about lakes? So, just to remind you here, I like this, what I call paleogeographies. So, just to remind you again and again, is I will look at this model system and we try to make models of the deposits, because we have to solve problems like this. You see in the right here, this is what the Cretaceous was looking across kind of North America, Central America time, and the basins were in different positions. Our basins were accumulating sediments. The rivers were coming in different directions. So you have here Texas. There were rivers coming off what was their mountain range, similar to today's, but then they're coming into this interior seaway. So that's where most of the sediments accumulated. Those rocks that you go and look in Utah, where I go with students, in Utah, Wyoming, all the way Montana, Canada, all of the systems that we looked at, they're fluvial and deltaic, were along this western interior seaway, what's called. And some of those systems produce now in Colorado, again, Wyoming, Canada. So the questions are, where were the rivers, or what were the positional environments there? And you can't get very detailed maps. This is what you have kind of global scale. So even worse, if you go farther back into early Permian, for example, here, this is how North America was looking at. It's even kind of rotated. Here was a equator actually. So Texas is kind of outlined there. So we were a bit farther south. And then there were large basins here into what I'm sure you heard about Permian Basin. And so there was some Permian time basins into what is now West Texas here. And then the rivers were coming from, because we're talking about rivers here, that's why I emphasize that, is it coming from Ouachita mountain range, was somewhere here, which was linked with the Appalachians. And they were coming from northeast, and also from south, some of them. But part of the northern area of our Permian basins was Aeolian and evaporites. Carbonate system, so completely different. Anyway, when you got into more detail on this map, wherever your reservoir is, or you try to understand, from large maps like that, you have to come down to those depositional systems, like rivers, things like that. Okay. We go back and continue with the fluvial systems. So the fluvial systems, we mean river systems, again, fluvial, the word's coming from Latin. But the way to understand this, any river systems. Okay. We'll have a catchment area or the drainage basin. So that's where the water is collected. And it's eroding the sediment and is moving it down the channels. Now, where you accumulate the sediment transported by rivers into what is called an alluvial plain area. So you erode from mostly the high relief area into the catchment, the water catchment, and then water is flowing through the channels, what we know rivers, and then it's deposited into the lower part of the system, and the alluvial. And eventually we'll see that maybe next lecture, some of the rivers reach a lake or a sea forming deltas. But some of the sediments stay behind into the fluvial system, so the river. So how happening that? So you have water flowing through channels, transporting the sediments, like the way we discussed previously. You can erode the substrate, take the sediment up, or you can deposit it. But how happen that you accumulate for a long time? What do you think is making that? What is the main driver? So, if we make some mountains here and it's going out to the sea, and then it's water flowing here, and I can make some channels. And so the water is going through these channels, and in the detail is that the base of the bed, and then has sediments. And you can see this with the velocity is picking up some and is depositing some form in bed forms. But what is making it to have this preserved tens and hundreds of meters thick fluvial deposits? What we call it? Any idea how that might happen? What's happening with the surface through time? Is it going up or down? Down. So if we have what is called subsidence, and the surface of the Earth moving up and down, as you learned from other classes. So if this is subsiding, it's creating new, let's say, new space for the sediments that they're coming through. So in general, the sediments are bypassing this area to the river flow, but some of it is left behind just because over a long time the surface is subsiding. Okay? It's subsiding too fast, faster than the sediments coming, it might form a lake. Okay? So subsidence, it's important. So if this area is subsiding faster than the sediments are passing through, you might form a lake here. Okay? So that's why in this area here, because of the higher subsidence before reaching the basin, some of this, river transported sediments might be preserved there. And we'll look at how those sediments will look in detail. First, again, we start with the modern river systems, and here you have some questions like this into your source to think exercise. And what you're asked to look at is the geometry of the channels, or the shape, and how the rivers look like, and we have different names for different morphologies. And some of these morphologies are linked with that sediment load, suspended load or bed load. Do you remember the way you transport the sediments through a flow? So here there are some typical river patterns or channel patterns, river channels. So if you have this kind of the water flow through multiple channels with kind of sediment bars in between, we call that a braided system. If you have a channel that is kind of sinuous like that, we call it meandering. Okay? That will be a meandering system. Then you can have something which in between that's called anastomosing. So you have channels that they kind of break and come together, but they're still a bit sinuous, so you call it anastomosing. And there are some conditions when the channels, instead to be sinuous like that, highly meandering system, it's more or less straight. It's never perfectly straight, but it will be straight. So we discuss mainly braided meandering systems and a bit on straight systems. But for you, it's good to separate between meandering and braided. And we'll discuss why. Is because the sediments accumulated in these channels will be different, the sandbars. And I hope that you will stay with you the idea of, how we recognize some of the sand bodies within the fluvial systems compared with, let's say, marine systems. So here there are images from Google Earth, and you, on your own river that you have to look, you will look probably at images like that. You can zoom in and out. The question is, which one is sinuous, which one is braided? Okay. So Colville River, is that this one? Is it a braided or a sinuous?
Braided.
Okay, you got the idea. It's looking more like that. How about this area? They're looking more sinuous. So one is braided, one is meandering. So there are different streams, and we can discuss that. It's maybe this is coarser, higher discharge. Here is some older channel that there might be abandoned. The same here. This will be sinuous and meandering. So Mackenzie River, a large river again into North America, into the Arctic, is braided. If you look at this channel system here. So this is also probably, we'll call it meandering here. Mississippi, we know it. It's coming down to Gulf of Mexico. You have scales here also to note that these channels are quite wide. Okay, so they're kilometers wide. To walk it, it will take a long time just to walk it across. Okay? So, and the size of the river, as you see, it's also telling us something about the size of the sandbars. Bigger the rivers, bigger the bars. Remember, some of these bar units will be at the scale of your reservoirs. Okay? The size, the dimensions, like kilometers across, and the thickness. Well, what do you guess the thickness of the bars will be? How thick the bars will be, you think? Any idea? So it will be 1 meter. How thick will it be? But what we can scale the bar to? The channel depth. Okay, so you accumulate the sand here, the thickness of the bar will be the depth of the river. Okay. And then eventually the top of the bar is coming to the surface. So how deep is the Mississippi River? That will be one of the continental rivers, quite large. So that will give you an upper limit of how thick these bars can get. Is it 1 meter? 10 meters? 100 meters? It's about 10 meters. Maybe deeper than that, maybe 20 meters in places. But, and that's how thick some of these bars might get. But that's a large river. Smaller rivers, any river you can think, like Colorado here, if you go downstream from us, Brazos, they will be just a few meters thick bars. And that's your kind of sand thickness unit, if you want. Okay, so according to the type of the bed load, to the sediment load, being bed load or suspended load, you can separate them into the pattern. So for example, the braided streams that you saw, typically they have higher sand than mud. And they also, I will add, they're a bit steeper in terms of the gradient, and this linked with this coarser grains. The mixed load system, that means maybe they have both bed load as sand and maybe mud as suspended load. They will form these meandering systems. And if you don't have much sand, but it's mostly mud transported through within suspension, you might form more straight channels. And that's typically for, you see when we get closer to the shoreline, we have what is called distributary systems. So the channels start splitting and getting more straight. Okay, let's look at some characteristic of this meandering versus braided system. So meandering is, again, you see this pattern all across Mississippi. It's easier to look, it's large enough you can pick this, the channel, and you see some lines associated with that. What do you think these things are? Previous path, but it's not only the path, it's emphasizing the bank, okay, usually the inner bank of the channel, and this is what we call a point bar, okay, so it's a sandbar, but it's attached to a point on the side of the channel, and when the channel is migrating through erosion on one side, it's accumulating sediments on the other side. Okay? And it's doing that at each bend. As some of the bends are migrating, they might kind of cut each other, and then it's kind of straightening the channel a bit, and it's abandoning part of the bend. And this is happening continuously, and then as they migrate laterally, remember the basin is subsiding also, so it's preserving some of the deposits. And that's what someone here worked. These are it's Rio Grande. I was about to say Mississippi. They have similar studies for Mississippi where you can map the location of the channel and then kind of date, maybe some old maps, or you can do dating of the sediments. And these are the different patterns of different years of the Rio Grande River. Okay, so each of these channel location was associated with some bars or point bars associated with it. So it's something that, because again the sand is accumulated into these point bars into the bend, you want to know how sinuous your channel is, because each of this bend will accumulate sands. So this defines a sinuosity number, which is simple. It's just the channel length. See how long is the channel if you follow the water versus a straight or down valley length. Higher the number, more higher the sinuosity is. You have to go longer distance along the channels to reach a point downstream. So here there are more examples of this. Oh, this is difficult. Let's see. So first is just the river here, and here it's showing the channel is migrating through time through different years. And here it's like small animations where satellite images were taken from 80s, like 84 till 2016. And they were just plotted on the top of each other. And then you'll see if you follow a river here, it's migrating. All of the whitish thing will be sand accumulated at the bends in those point bars. And then you follow one of the channels, maybe somewhere here, but there are multiple places. As meander is migrating, it's reaching the channel in the upstream and is making a cutoff, what is called. So some of these bends are abandoned and preserved essentially. And the idea is you can do, there are numerical models that kind of mimic this pattern here. And these are done to, here it's a scale, but the idea is to understand what's controlling the migration pattern, how fast they go, and where the sediments might accumulate, laterally. So, but why do we have, what's happening with one bend? Why the bends are migrating? So, in one of these things, in one of the bends, we define the outer bank of the river of the channel as a cut bank, and the point bar where it's accumulating, we call it the sedimentation side. And we look closer what's happening with the water flow around one of these bends and why it's eroding on the outside and how it's depositing on the inner side. Because that's critical to understand where the sediments are accumulating and how that looks like in terms of sedimentary structure and character. Because that's what all of this meandering system is, point bars. Accumulation of the sediments along the bends. So here it's a cross section. I will show you more of these things from different books to be sure you understand the idea. And then each of them, they emphasize different things. So here is the surface of one channel, and it's a cross section. Here is the bottom, and at the very top you have what's called the maximum velocity. So notice where is the velocity. If you look within the channel, where is the maximum velocity? Is it which side of the channel, you think? On the outside, you see, so it's not on the center. And it's kind of the upper part. Okay. And the turbulence, so that means is where the sediment is mostly, it's also on the outside of on the cut bank, what is called. Now, within the bend, if you remember any sinuous channels, it has one bend, and then it's getting a bit straight and it has a bend on the other side, okay, because that's giving us the sinuosity. So before going to the next bend, it actually has a straight reach, and then the velocity there will be strongest in the middle. On the next bend, the velocity will be stronger on the other side. Okay, so this is something like this here. So you have a sinuous stream, and here it's showing a cross section, okay, with the velocities profile here. The arrows are showing the highest of the surface because of that shear stress. Remember that the bottom is coming to zero, but is decreasing. So a profile here is showing the strongest velocity maybe on the outside bank here. Here is maybe not trend on this straight reach, but when it's reaching the bend, it's getting strong on the outside. And there's something else happening. The velocity is going down, it's stronger on the outside bank, but the surface of the water, it's also going straight out to the outside bank. So that's because of the inertia. So you think when you go and you drive around the bend, what's happening with the car? Which way it tend to go? Tend to get out, isn't it, from inertia. So the same thing happening with the water here. So the water in the bend tends to go to the outer bank. And this piling, the surface is a bit higher on that side. But when it's getting higher, the gravity will tend to take it down as it's going around the bend. So the water, in other words, here is coming up, tend to go down, and then it's going up on the next bend. So the water within the channel actually, it has this kind of corkscrew trajectory. So it's going up on the outside bend, then it's coming down, it's going up on the other bend. And by doing that, that's the way it's taking the sediments also. So it's eroding the cut bank, the outer bank, and it's taking the sediments on the inner bank. It's putting into the, let's say, the point bar there, and it's doing the same thing on the next bend. So here it's another diagram. You can look over this and see which one you prefer. These are from different textbooks, but it's showing us the same idea now with like a 3D block diagram. So here is the channel, so the flow is going, it's the red arrow showing, and here what they actually show, these smaller lines, is the flows at the bottom of the channel. Okay, so because the water is going up on the outer bank, then like I say, it's going down at the bottom and up to the next bend. So then it's taking the sediments from the deepest part of the channel, kind of oblique and up onto the other side. So here it's showing something else. you have now bed forms within the channels. Okay? So the strongest velocities are on the outside in the deeper part of the channels, and as you come into the sides, onto the point back side, the velocity is decreasing. Because of that, you have larger bed forms onto the bottom, deeper part, and you have smaller bed forms like ripples we discussed as you come higher up on the bank. Okay. But something else happened. Remember, through time, this bank is migrating, it's eroding, and this bank is accreting, or is adding sediments. As you add the sediments, you end up with a pile of sediments here that at the bottom will record the type of the sediments that are deepest in the channel. Higher up onto this, you have sediments that are kind of higher on the bank. And if you go even higher at the surface, you preserve whatever is there. So when I'll show you point bar deposits, the way they look, it's a consequence of the migration of these channels and then the way they accumulate sediments on the inner bank. So besides this point bar deposits, there are other elements within this meandering system. So the point bars are the most important. They will discuss more about that because that's where the sand is preserving. But then there are other elements that you might recognize, on the subsurface or the outcrops when you look at the meandering streams. So some of them are called like levees. So levees are just the higher edges or the banks of the channels. So that's what is holding the channel in. So how do you build the levee? I mean, not by engineering, just putting material up. But how do you think the river is building the levees? These higher ridges. Any idea? Say?
I studied it.
The sediment, but how the sediment is getting there? Through the floods. When the river, it's getting high discharge, the water level is reaching the bank and is spilling over. During the floods, you put another layer of sediments on the banks. And then the river is getting down. Most of the time, it's flowing below that level. But each flood is adding to the levees. And that there are some problems when I say we, like humans, we try to control this flood. If you don't let the river flood anymore, it's not building the levees by itself. So you have to do it yourself. Okay. Anyway, so floodplains is all the material that it's in between the river channels and it's outside here. What do you think is dominated by? Is it sand, mud? What is a floodplain made of? Is it coarse material or fine material? Fine, you have it. So it's called floodplain. It has water across during the flood times. And the material that's coming out of the river is mostly fine. Clay, silt. And what else is obvious onto the floodplains that will make us to recognize this type of environment? Agriculture, but in older time, there's no one necessarily farming during Cretaceous, but it's just vegetation. Okay? So when you have whatever wood fragments or roots, anything like that, you're on the floodplain. Okay? So this is something else. During the floods, we might breach the levees, so we break through those naturally built high ridges on the sides, and when the water is breaking, passing through, it will form some channels with some splays, what we call crevasse splays. Maybe you saw it sometimes in the news when they say, oh, the levee was breached. When that's happening, it's like a channel cutting through, and the other side, it's forming like a small fan of sediments. That's called the crevasse splay. It's a disaster when happening in places where humans have businesses, but it's a natural phenomenon. And then there are abandoned channels, some old meander bends that they were cut off by channel migrations. So So these are kind of different elements. What kind of material do you think those abandoned channels is filled? Is it sand or mud? Say?
Sand.
Well, the sand is within the point bars, okay? But the empty channels, which is just left abandoned, eventually will fill with mud through time. Okay, from the floods again. So they form, you see some they call oxbow lakes. They're still, maybe this one, you see it's isolated completely in old bend. But now it sits empty there and it's just accumulating mud from floods probably. They call it plug channels, mud plugs sometimes. So it's important to understand this because that's not a good reservoir but might be a good barrier or seal for your reservoir. Okay, so meandering streams here, it's not a diagram. We don't have to go in detail, but it's emphasizing some of these elements we keep saying here. See, the point bar is the most important because that's where the sand is. And you know now because the flow type, it's eroding the outer bank, but it's accumulating sediments on the inner bank. And it's doing that around each bend. Then you have the levees around the bends there, and all the elements we discussed. Something else here we introduced on this slide. So one is, and we'll know why, we'll look into why and you'll know, is that the point bars on the log or on the rock preserve will have the coarsest sediments at the bottom and the finest at the top. And on the well logs that telling you different properties of the rocks, you have what we call a fining up pattern. So that's telling us the coarsest deposits are at the bottom and the finest at the top. And that's typical for point bars, typical for fluvial systems. And it's important. It will be important for you throughout your career if you work in such systems. Now it's something else. As the point bar is migrating, you see it's forming this sand bodies that migrating through time will in a 3D space will form like larger sand bodies, and because subsidence they accumulate on the top of each other and lateral to each other, will form what we call channel belts. So there will be belts of these sand accumulations along the channel. Okay, so more about why the point bars have this fining up pattern. Why is the coarser sediments at the bottom finer to the top? That should stick with you for a long time. Again, the idea is if you have the flow, channel flow lines around the bend, have this kind of circular movement through the channel, and that's higher velocity is in deeper part, and then is decreasing as you go up. And because of that, the coarser deposits will be at the bottom. Here it's called even the gravel, they emphasize it can be gravel or coarse sand. Then higher up you have plain parallel and then trough cross strata. So that will be our cross strata that we're discussing about. Okay? And what is giving us the flow conditions and direction. And then as you go higher up along that side of the bank, the point bar have ripple laminations. And if you go at the very top of the bar, you might start having some of that vegetation and ripples. You know, small ripples from floods maybe and vegetation accumulation. All of that in a single vertical succession will show up as coarse with maybe gravels, and then will be cross strata, and then ripples, and then it will be even finer silts and clays at the top. So all of that is giving us this fining up pattern. This is typical for fluvial systems, and more specifically maybe for meandering streams. So here it's again a kind of cross section right now. So it's a low water. The channel is located here. At the high water, the water might get outside the channel and building these levees. Okay. if you cut through what we call the point bar again, this is how you expect to see the sedimentary structures and the deposits. So we'll be cautious at the bottom because it's the location of the bottom of the channel as migrated through time. And then we have coarser and larger bed forms like dunes, and then eventually vipals or flat laminations here, and then vipals, and then eventually the top of the bar, you get into the levee with vegetation. Right. There's some small channels associated with water cutting through the point bar. What is interesting, we have this line here, and sometimes you see that in the deposits, is that these are the timelines. This is the location of the inner bank through time. Okay, so the channel was somewhere here, and then migrated, and the channel was there, and it was there. As the channel migrates, that's why we accumulate sediments here. Is that clear? This is just a 2D, but these things happen in kind of a 3D geometry. They're trying hardly to understand the geometry and migrations of this up in Canada, where they have those tar sands in the pits of Alberta. So all of their deposits there, I think, is Lower Cretaceous. They have large point bar systems like that. Large means 10, 20 meters or more thick. They were large rivers. And all of this, all of the hydrocarbons are into point bars like this. Okay? And they're mining it. So the surface enough that you have to kind of dig it up. But even so, you have to know the geometry of this point bars, you know, to maximize your digging effort or the mining effort. Or sometimes from the quarries they go shallow in the subsurface and they have to drill shallow wells and steam them and follow how the flow is going. Here it's an example. So it's called the McMurray Formation, so they're point bars in Cretaceous. And here they're some of the logs. This is wireline logs, that's what you might have, all what you might have in the subsurface. And look how someone interpreted these things. They say, well, here it's a wireline log, and because you don't say here, let's say it's gamma ray, so in gamma ray there you have lower gamma ray, here is telling you the sand, you have another one there, and then here the sands are thin, and they think, oh, all of these are connected like this, and all of this will be one of the point bar deposits. Here it's one of the abandoned channel filled with mud. And then because of this is a point bar, they even put some lines through it. This is just model river. You can't really see that. But they know, oh, if this is a point bar, then the point bar was accreting this direction, and you will have some surfaces to that. And the problem is, they have this problem there, these surfaces might be lined with mud or finer deposits. So if you want to, to produce through this a reservoir as such, see, notice the scale here, 0.5 kilometers. So this will be, 3 kilometers across, 4. If you try to produce this, you have to wonder what some of these muds will do to your fluid flow. And this is just a 2D, but they have this problem in a 3D, and then it's point bar at the top of a point bar. And it's getting more complex, as you see here. Okay. So this is all of the data you might have, just one wire log like that, but where the sand and mud is, and from the geometry and the models we learned from the modern or outcrops, you have to make sense of it. So here it's an example. This is on the side of the road here, which is, we think it's a point bar. This might be Wilcox, do they say? No, Wilcox. So Paleocene, Eocene rivers flowing into Gulf of Mexico. This is not like a textbook. It's just some sand there with some surfaces. But which way the paleoflow was oriented if I tell you this is a point bar? Not very thick, just a few meters. which way the flow is going? Left to right? No. So if this is a side, of the point bar, and the channel is migrating like this, which way the flow is going? Through the channel. Into or out of page. Everyone get it? This is like a cross section. So this is similar to this. Okay, so the channel was there, and the point bar, the surfaces you saw were just kind of lateral accretion. And the channel was somewhere in or out of page. I know, this looked not so nice, but sometimes that's what you have to interpret. So the surfaces will be point bars, and the channel is there. How we will know that for sure? Looking at the outcrops. If there will be any bed forms like dunes, cross strata, or ripple laminations within the rocks here, we go and measure, and then they should show us that the flow indeed is coming kind of out this direction. Kind of high angle to what we interpret as accretion surfaces. Okay, so let's say the maybe flow is coming through this. And again, why it's important, here the top is from a study. They have the porosity modeling of some point bar deposits. So with the light color, higher porosity. And they emphasize if you have one of these geometries of the point bar in a meandering stream deposits, the higher porosity will be at the bottom, and sometimes following some of these accretion surfaces. Okay. And then whereas lower might be finer, muddier rocks. So notice they get finer to the top there, but nevertheless they follow some of these accretion surfaces. So again, what to remember? The fluvial meandering streams, they have this fining up pattern, and that's because here you record the bottom of the channel, maybe erosional, with the coarser material. As you go up, there are larger bed forms because higher velocity, stronger currents at the bottom. As you go up, you get maybe smaller bed forms, maybe ripples, and then the floodplain will be more or less the top of your bar. In the well logs, if you have any well logs, electrical or gamma, will have this fining up pattern, or bell shape, what they call it. Okay. The abandoned channels, they're elements. So, like I say, if you have a cutoff here, and one of the channel kind of stay filled with water, but no flow through it anymore, then it's filled with mud, and it's called mud plug sometimes. Okay. So initially we call that an oxbow lake. So it's kind of isolated body of water as a lake, small compared with what we discussed earlier. But then all of that is eventually filled with mud coming off the main channel through floods. And in Oxbow Lake here, more detail on the aerial photos, probably over the Mississippi. So here it's an Oxbow Lake with all of the other elements that you see here. So the main channels is somewhere on the right. They have a lot of annotations of this because probably this is a 50s aerial photo map. Do you know why the whole country, all countries actually, not only US, they started in the 50s to collect these aerial photos, great detail like this? What was the reason for that? The spy satellites. In the 50s, no one was thinking about that. It was too early, but it's good thinking. They eventually did that. So to make topographic maps, see the ones that now we don't even use them anymore, for the elevation, right after the Second World War, everyone started to do this. I mean, they had all the planes and the technology from spying, like you said, during the war. And they were getting high detailed maps like that. I mean, photographic maps first. And then from that, they were doing extracting the elevation. However, images like that in great detail are showing us this. The main channel, an abandoned channel, Oxbow Lake, filled with mud maybe in the future. And then the levees, look, they have natural levee here, the higher banks of the channels. And here, what is this thing, you think? The splays, the crevasse splays. You see, during the flood, there's water coming out and is forming this crevasse splays. Are the crevasse splays good reservoirs, you think, or not? Here it's another image from Ob River in Russia with a crevasse splay. Are these crevasse splay good reservoir, you think, or not? No, someone say no. Why that? Well, how thick the crevasse splay deposit you expect to be? How thick? Again, you can say 1 meter, 10 meter, 100 meter. Someone say 1 meter. So it's probably meters. It's just they get as thick as the elevation of these levees against the floodplain. See the difference in that elevation, it might give you how thick the crevasse splays can get, because that's all the space or accommodation they have here. And then they are a few kilometers across, some of the large ones, but they're relatively thin. So they might form reservoirs, but not very large reservoirs. And again, here it's another 3D diagram to show all of these elements. The point bars, you know, the levees and the crevasse splays. And again, the crevasse splays form into the floodplain, not very thick and not very large exactly. So, as the channels migrate here, it's a diagram, you form one of this, what we call a channel belt now. Okay, so they're formed by multiple of these point bars that migrate through time, and then they might be connected to each other laterally. And then these are older channel belts now that they are accumulated because of the higher subsidence in the basin. Okay. So, what is a channel belt? And maybe this is the last slide. This or next. This is important, you know. So, from the reservoir point of view, channel belt is more important than the channel. So, the multiple point bars that accumulate migrating laterally, they're more important than the channel or one point bar. Why is that, you think? Why we emphasize that? Is because in a subsurface it's hard to actually recognize one channel. And usually you recognize this accumulation of multiple point bars, and we call that the channel belt. You never know you're the same channel or it's one channel or multiple that migrated through time. So all of this sand accumulation in relation with one channel migrating, we call that channel belts. And the channel belts will be larger accumulations, and they're large enough, you know, kilometers across. Here it's an example from Brazos. Here's the Brazos River, and here is an older path of the Brazos River with all of the abandoned channels and point bars. So this will be a channel belt, and now the Brazos is building another channel belt. In the subsurface, that's where you can recognize because of the resolution. You hit some of these point bar signs and say, well, you hit a channel, you say, but most likely you start mapping that extent of the sandstone body or the river system and call it the channel belt. Okay. And we continue from here next time. Thank you.